Hello everybody, so this is the second session of Hadoop tutorials prepared by CERN Hadoop IT service. So in the link to the first one you can find on the bottom of the screen. It should appear right now. And today we'll focus on data ingestion to Hadoop. So we'll cover actually two types of data ingestions. One is the batch ingestions, which means that you have already your data somewhere produced and you want to bring it to Hadoop in one-off action or repeatable action, but it's not in real time. And the second type of ingestion is almost near real-time ingestion that we'll cover in the steps in the second part of this tutorial. So let's move quickly to the batch ingestion. So of course, if you want to store your files on HDFS, you can just use the HDFS command line interface like HDFS DFS put. Of course, this is not very exciting one. So actually, we'll cover different tool which brings you more functionalities and performance, which is actually Kite. So what is Kite? Is a high-level data API for Hadoop that is able to during the ingestion already convert your data to a different format like Parquet, Avro, and can also partition your data, can do small restructuring of your data. Basically, I think this is the one definitely to recommend if you want to ingest your structured data, because you need to have a structured data. It cannot be unstructured data. If you want to bring your structured data to a Hadoop data file system. There is also good news. We put our repository on GitLab, so all the steps that we are doing right now, you can actually download them with a quick single step by just running git clone. So you just run it, and you have all the steps that we did in the previous session, plus the current one, which is session number 2, data ingestion. So we move to the Kite, which is under 0 batch ingestion, so Kite. And first of all, as I said, we need to get the data. So we already prepared them, so they are on our HDFS. So we just bring them to the local file system with HDFS DFS get, and I just show you. So those are data that were downloaded from files group grouplens.org that are providing some CSV's data. So we just use a random one for this demonstration. Now what you can see, we have four columns there, which actually represent the records of the movies ratings. Yes, so if we want to use Kite to store them on HDFS, first of all, we need to actually get the schema of our data set. So one good thing is that Kite actually provides an infrastructure to get it automatically. So if you have CSV, you just run command kite dataset CSV schema. You provide your CSV with your data. You just provide what is the record name. This is a metadata information, and then as an output you will have your data schema written in JSON, which is compatible with the Avro schema. So this is our schema automatically extracted from our data with KiteSDK. So we have, as you can see, 4 columns: user ID, movie ID, rating, and timestamp. And also Kite automatically detected what are the data types for it. So once we have schema for our data, what we want to do, because we want to actually partition our data by year, so we need to also create a schema for the partition. So it's kind of a schema policy. So how you can do it, you can just provide a file which is a JSON format, and it looks like this. So you say that our data will be partitioned yearly, and this is the syntax for the file, and the time to the data of the partitioning should be taken from the timestamp column from our records, and then we write it to the partition policy JSON file. So finally, once we have a schema and partition policy, we have to initialize a so-called data set. So we do it with another Kite dataset create dataset command, which actually you have to provide a location on HDFS where your dataset will be stored, your data schema, and also the type of the file format that you want to store into on HDFS, plus the partition policy JSON file that we have just created. Yes. So once the command is executed and finished successfully, we can see what happened actually on our HDFS. So our dataset on HDFS was initialized, so we can see that there is a subdirectory called metadata, which actually it has all the information that we provided. So it has a schema and description, which also says what contains all other metadata about our dataset. So once we have a data store, finally we can load the data, which you do with the command kite dataset CSV import. Yes, you provide the CSV file to import and the target dataset location, and that's it. And then you have Kite output from Kite, which actually informs you that it's working on your dataset and loading it. So there is a big output out of it. Okay, so it finished. So according to that, all our data should be already from CSV should be stored into HDFS, partitioned by year based on the timestamp column, and stored as Parquet data format. So we have a script show data, which actually gives you the idea what is there. So first of all, we just check what is the content of the directory that we checked before. So you can see that it was already populated with the subdirectories, which actually are representing our partitions. And inside of these directories, we see Parquet files. So this means that, okay, all our data were partitioned well, and then we have the Parquet files in each partition. And there is extra command just to show you, which is kite dataset show dataset, which actually can sample your data from your Parquet file. So you just provide the location of your data set, and then it will sample the data. So this is the output of it. So you can see, yes, our data are there, our movies ratings are there with the timestamp and so on. So in the second part, we'll demonstrate how to use Sqoop in order to move data between your relational database, in this case would be Oracle, to your HDFS. So we change the directory in our repository to Sqoop, and here we have files. So first of all, we'll show how to run an ad hoc single Sqoop job. So basically, Sqoop normally is installed in most of the distributions, including Cloudera distribution, and you just interface with it normally with a command line interface. So if we want to import the data from a database, we just run a Sqoop import module. And then definitely what we recommend is to use a direct connector for certain database vendors, because it improves the performance and reduce the footprint, which can cause the extracting of a data from a given database. So there are direct connectors for different direct connectors for different databases. In case of Oracle, there is Hadoop, which we will use today. And if you want to use Hadoop, you just explicitly need to mention this direct. Yes, later you need to point where exactly your database is. So you need to provide free details about location of your database. So first of all, host, port, and the service. So the service is an endpoint, which is under which database is running, and you can connect to it. Then the username, in this case, will extract meetup data, which we use in the first session of this tutorial. So the username on the database is meetup. -p means that we don't want to put our password inline. This is important, because if you put it inline, somebody else just by running ps command can actually see the password put as an argument to your program. So it's not recommended to put inline your password. So we'll put it in interactively when specifying -p. And finally, on the database, we need to specify from which table we want to extract the data, how many multiple sessions we want to use to extract data. Of course, the more sessions we set, most likely the faster import will be. However, you need to find a trade-off, whether you want to how much you want to hammer your database with parallel sessions. Definitely recommend not to put too high numbers. I think 2 for small data sets like we have here is good enough. And the last but not least, the parameter where actually we'll put our data. So on HDFS. So on HDFS, we'll put it as meetup data Sqoop under our home directory. So I just executed this command. So it is asking me for password because we specify -p. So I'm inputting the password, and then Sqoop starts working. So you can see it's very verbose. It's saying that it will use data connector for Oracle. And Sqoop uses MapReduce. So basically our MapReduce job started and to extract the data from a database. So it was pretty fast because we have just 500,000 of records. In total it was 206 megabytes, and we haven't specified what target format we want to choose. So by default, Sqoop exports everything to a text data. And this you can see, okay, when looking into our HDFS folder, you can see that we have 2 files with the data plus an empty file. In these files, you have your text data. Why there are 2 files? Because each mapper, so each session of Sqoop produces 1. Yes. So if you want to have just 1 file, you have to go for 1 mapper. If you want to have more, well, if you start more sessions, you will have more files in the target directory. And then I'm just displaying the content of one of the files. You can see that really there are data comma separated, so it's a text. So I just executed the command cat on HDFS file. Okay, so that was ad hoc example how you just use how you set up one of import task. Now we're gonna show you how you can set up a Sqoop job, because Sqoop provides a kind of infrastructure that can keep your metadata of your extractions on the HDFS, so you don't have to always specify these parameters like connection string. Yes, if you want to run multiple times the same extraction, because okay, by default Sqoop only snapshots the current state of your table. Yes, if you want in future to your table has grown and has more rows, and you want to synchronize it with HDFS, most likely you will need to run yet another Sqoop job. So that's why it is worth keeping your argument somewhere. Second. So I will show you how to create this job. So first of all, we'll remove the first and then the output of the first step that we did. So the Sqoop job you create with Sqoop job command, and then you specify the name of your job. You say what kind of job it will be. It will be import. You can store all your parameters already there. Yes, so what user, all the things that we say. This time we will export the data into Parquet format, and then it requires, when you are creating it, it requires to provide the password. So I did it. Then I listed my jobs, so you can see there is already one. And then I'm looking into my job properties by just executing Sqoop job show and my job. And then you can see all the parameters that were set for my job. This just instantiates a job, but it doesn't execute it. Yes. So if you want to execute it, there is another command, which I will show you right now, is just Sqoop job execute, and then you provide your job name. And this is good enough for a snapshotting of your table, but what we want to show you today is also how to make the incremental import of your data. So imagine that there were a couple of rows inserted for yesterday, and we did an export 2 days ago, and we just want to get the newest rows. Yes. This is not a trivial because, okay, by default, Sqoop does not detect the changes, doesn't detect the delta. So you need to tell him how he can do it. So in this case, we will do it manually. So we just say, we know that there is a mtime column in our table in a database that actually represents where the record was inserted. So this is the column. So we can provide an extra argument to our job that that is saying, please use this predicate between on our column, which represents the day of the insertion, between certain values. Yes, and no, those values are expressed in the timestamp. So because okay, I'm doing it manually, I have to calculate what is my start timestamp and stop timestamp. You can see it here. So I'm keeping the recently exported data with the timestamp in a checkpoint file. And if this checkpoint file does not exist, it means that actually I never ran my job before. It will be created at the end of the job. But if it doesn't exist, I'm just initialize this one with 0, and then I'm saying, please export everything until today midnight. Yes, and then I'm providing this parameters here, and at the same time, I'm also modifying the target directory to represent the day of the last row imported to my HDFS. So if I just execute this, you will see, okay, I need to provide a password, yes, because I want to do it. Okay, the export is running. Basically, initially it will copy entire data set, so we should have the output the same like during last execution of Sqoop. So all this 500,000 rows should be imported. Okay, yes, we have the rows. So you can see that I'm already listing the content of our output. So here you can see that there are two Parquet files created for my data. So they are reasonably smaller than the text file, of course. Additionally, what you can see is the directories with the meta, which actually is the same like we use in the previous step with Kite. Because actually what Sqoop uses to store the data in Parquet and Afro format is this Kite API. So that's why we can even use Kite to see what the data were imported there. Okay, so this is nice, yes, because it imported. So if you run this job again, we shouldn't have new rows because we have already the checkpoint file, which will tell that we do not have to. And of course, actually, our job will fail because it is saying, okay, I cannot insert the data to the same directory because each job has to have exclusive directory as an output. So this is another protection just to not run again the same thing. But just to demonstrate it, I will change that we want to export everything not from today but also from tomorrow. Yes. So of course there are no rows like this. But will automatically update the directory to the new one. Yes. So the MapReduce is starting. Is scanning the data for the data that were inserted between today midnight and tomorrow midnight, and of course there are no new rows, just small ones. Small data received 0 records, and just metadata were created for the new day. You see, so that this one is empty. Okay, so that's it for the Sqoop. So the next one will move to a more exciting topic, which will be real-time data ingestion.
So after covering some use cases with batch imports with Sqoop and other library as Kite, we are covering a tool which is closer to real-time processing, real-time data ingestion, and it's Apache Flume. Apache Flume is a data transfer engine driven by events, and what we will show today is several deployments, different examples that what you can do with Apache Flume. So the first one that we are showing today is gonna be a chat. So a chat, and where every client will have will use a Flume agent, and then we will have like a main Flume agent, which we will call a gateway, that we will use to collect all the messages from all the events produced by the clients, and then we will write all the messages that we receive into two sinks. In that case, one it will be HDFS, and we will write locally also the data that we are receiving. For every of our agents, we will have a source, and the source that we will use is netcat, and this source is quite simple. It's just opening a socket. We will expect some data, and as soon as it receives an end of line, it will create an event with the data that was previously received. So basically, each line will become a Flume event. This Flume event will go to the channel, in that case memory, and the arrow sync will send that event to our main agent, let's say, and then it will be written to HDFS and locally. So if we go to our console and we go to the repo, the data for the second tutorial and our first example, we have like two different environments. No, one is the gateway and another one is the client. For the gateway, we should deploy first the gateway, and then we deploy the agents that will connect with the gateway, with our main Flume agent, let's say. So in conf, we have different files. The first one is the agent.conf, that is for configuring the agent. The second one is just to set, I can show it to you, is just to set some environment variables that the agent needs. So basically some the Java home and the options for the Java virtual machine. The third one is just for logins properties, so what we want to show in the console once we run the agents. And the most interesting one, let's say, is the agent config. What we specify here is the different components that will, let's say, build our agent. No, so we have the arrow source that will receive all the events for other agents. And the arrow source will listen in all the network, our networks, no, with the 0000, and will listen in that port. And then we have placed interceptors. Interceptors is another component that will intercept our events and will modify them or drop them. In our case, we have implemented a custom interceptor. This custom, let's say, you can customize sources, channels, or sinks, but you can also implement interceptors. There are some built-in, but the one that we have implemented basically take each event and add a timestamp in the beginning. So since we are building a chat, we want to see the time when events are coming. No? Okay, then we have we need to declare the memory channel, the capacity, and the transaction capacity, because events are written in the channel and read by using transactions, just to be more reliable. But we need to declare two channels, because per sync we need one channel. So we need one channel for HDFS and we need another channel for the local sync. Here we have in the source we have specified both channel, and we have specified also the way that we want to write to that channel. And the way is replication. So we want to write the same to every single channel that we specify in channels. So in that case, we will replicate every event that we receive through this port and bin address to this channel and this channel. So basically it will be replicated. And then finally we configure our two syncs. One for HDFS that will take events from the HDFS channel and will write our data as text. We specify that it will be text here as data stream, and it will write the files here in TMP on HDFS, but in the folder TMP from chat data. And the same locally. It will write on this machine into a TMP from chat data. So, as I mentioned, we have implemented something. What we have implemented is this interceptor that is in source. So we can have a quick look to this interceptor. But basically, what it does, let's say the most important method is that one, where we intercept the events we basically convert the body of the event into a string, and we concatenate the current time, basically. And then we produce another event that is return, and is the way that we intercept events. If we send null, it would be the way to drop events. The rest is just some bureaucracy that you have to do when you implement in interceptor. Okay, so since we have implemented something, we have the source code, we would need to compile it, basically with javac, and then we can run our agent. How we run our agent? So we have we would need to create the local directory where the data is going to be written, and then we start the agent with Flume. We should say that we are starting as an agent. Then we specify the class path. The class path has just been created when we have compiled our class. Conf is the configuration directory to take the files that we were describing previously. The name of our agent, basically the name that we have used to declare, to configure our agent. It shouldn't be the same as here. And then we point to the configuration file. So if we run this script, we start the agent. Well, while this is starting, we can move to one client, to deploy one of the clients that will connect with this gateway. So if we go to the Flume chatbot client, we have a similar structure. So we have compile conf. In conf we have basically something quite similar, but we can have a look in the configuration, which is slightly different. So if we cut this, in that case we have the netcat source. So this is a source that basically opens a port, in that case that one, and it will just wait for data. So we will use telnet to send some data, and we will see how we can, let's say, interact with this port. No? And we have placed also a different interceptor that has been implemented by us as well. And in that case, what the interceptor does is add the username to the message. So the same idea with the timestamp, but in that case, we add the username. It needs to be done on the client side because it's where we know which is the user, and the timestamp could be is done on the server side, so where the gateway is. So this agent is much simple. Here we have just only one channel, one memory channel, and the sync is basically a sync that will write to this abroad source that the gateway has. So we point to the machines where we deploy the gateway and to the port that is open there. So the gateway has been started already and is just waiting for us to connect. Well, we can have a quick look to the interceptor, and basically if we go to the intercept method, what we have is, well, we got the username from the system get property username that represents the user that is logging, and then we concatenate this username with the body of the event. That is, it will be our message. So we need to compile that, and then we run the agent. We will run it in background, and then we will be able to start the chat. So as soon as our agent starts, okay. So we have our agent running and is listening, as you can see here, in the port 1, 2, 3, 4. So we have a script also that is generated when we run the agent init chat that basically open a telnet connection to the machine where we are running the the client, the Flume agent, so that machine, and the port that we are using. So we open a connection to the socket, and then we can basically write whatever we want. So these messages are being sent to the gateway. Okay, we can see here that the client got connected with the gateway, and we can do the same for another machine where one of my colleagues is connected, and then we can see how the messages differ one of each other, no? Because of the username and because of the timestamp. So if we do the same, we go to the first case to the client. We can deploy another. We will need to compile it, and then we run the agent background. So I can open another terminal where we can. So it has been started already, and we can now init the chat and write something different, no? Okay, so if we go now to the machine where the gateway is running, well, I don't want to stop this, so let's open another terminal, and then we can see in that machine that the data is coming to the directory where we said, which we said previously. So in TMP we can see, well, we have different files from previous tries that we did, but basically they are ordered by timestamp. So I would say in that one, well, since they are short, we can just cut them. Yeah, and we have the data we have just sent. So we have the data, well, they are not short. Okay, they are not short, but we have here the timestamp that was introduced by our gateway, by our main Flume agent, and that message was sent after the one that I sent from my username, and then we have here our the one that I sent. So also that data is coming to HDFS. So if we do HDFS DFS minus cat, we can see the same coming. No such. We will need to place double quotes because otherwise the cell will expand this path as it is local. And here is order, so it got the files in the proper order, and we can see here the same data from previous examples. Okay, so that's it for the first use case of the Flume chat, and now we can move to a better approach for this Flume chat, where we will use a broker of messages.
This step will demonstrate how to connect Flume agents with Apache Kafka. So what is Apache Kafka and why we want to do it is, first of all, Apache Kafka is a message broker which is distributed and is scalable and reliable. This means that you don't have only one single point of failure, like we had in the previous step when we, for example, were running a single gateway which was running on one machine. So if this gateway process for some reason is down, then this means that all our clients, all the client agents that are running to this gateway will have to wait, will have to buffer the messages in a channel, which ultimately will lead to buffers overflow and probably crash of entire system. So here where Apache Kafka can be very handy, because then you can think about this as like big buffer which is distributed across many machines that can actually first of all, you can insert the messages there, and then they can stay for a longer time, and then later you just consume them once you are ready for it. And so we are changing the predicate from the we are changing the paradigms from the push to pull. Yes. So once you stage your messages on the Apache Kafka message broker, then you can sync them to many other places. Like you can send them to HDFS, you can send them to Elasticsearch, you can do with them whatever you want. So it's a kind of, this changed our architecture of a chat from, instead of using Flume agent here, we just put Apache Kafka. Yes. Later on in the next step, we'll also show you how to, for example, sync the data in almost real time from Kafka to HDFS. But in this step, we just focus how we can configure these Flume agents to write to Kafka, and we will see the messages appearing on Apache Kafka with one command line tool. So we are switching to our console, and we go to part number 3. So what we have said, so again you have the config directory. Oh, sorry. So actually it's part number 2. What you can find here is, again, like in the previous one, we have the config directory, where you have agent configuration, which probably in this case is the most interesting part. So you can see that, okay, the first 2 lines are the same, but instead of having sync to a gateway, we put Kafka sync. Yes. So, and we declare the Kafka sync is, of course, we need to say what is the type. We still use a memory channel. And we also have to provide the broker list, so the list of the machines, at least one that where Kafka is running. Yes, because Kafka can run on 1, 2, or more machines, depends on the requirements. Yes, and Kafka message brokers comes with the let's say something which is called topic. So normally, if you want to write the data, you need to write them to a given topic. So it's like a container. This topic can be then partitioned again and distributed into many machines. But of course, you need to declare, okay, we are using Flume chat topic, and then also for the reader later on, if somebody would like to consume our messages, the consumer has to also connect to this Flume chat topic in order to read messages that we inserted. So and batch size, you can set how often we flash the data to the Kafka. So we just say, okay, every message we want to insert to Kafka. It is not too bad, because Kafka can consume, unlike HDFS, one after the other, one message after the other. There is no big problem with that. So one thing to add, that actually we move our interceptors, both interceptors, to the agent, to the client Flume agent. So we put in the client agent the user name into the message body, and also we put the timestamp. So this is something probably reasonable to do, because on the timestamp will be inserted immediately as the message was created. Not like in the previous example, it was added in the gateway. Okay, so that's it. Our Kafka, as you can see, okay, we have specified our Kafka cluster is running on the following machines, and it is already up, so we don't have to start it. So first of all, of course, we have to compile the classes for the interceptor because they are not yet compiled. And in another window, I will open, okay, and then in this one we'll start basically a consumer, a generic consumer for the messages. So this is provided together with Kafka. So this is a class that can connect to a given topic. So in our case, it's Flume chat, and get the messages. So they will be displayed on our screen interactively. So I will just execute this one. I will do it in the background. Okay, so it started. Okay. And then in another window, we can already start our client. So I don't remember if I compile it. So once we compile, we can already start the demonstration. So I will use two windows. I open a new one, which one is logged as a different user than the other. So first of all, what I have to do is to start agents on each of the machines. So they will listen on the netcat port and send whatever it is there to the Flume, to the Kafka cluster, and we'll use the tool that is able to see what messages are coming to our Kafka topic with this consume Kafka topic script. So I'm starting it. So in the background we should see if there is a new message. It should appear in our console. So right now there are of course no messages because we haven't started to insert anything. So right now we are starting the client for the chat. So we'll connect to the Flume agent which is listening, and we can already type the things. Here is client number 1. Okay, so we can see on both windows that this message was received by Kafka topic, and then it was broadcasted to both consumers. So we can also, here is client number 2. Sorry, I haven't started it. Here is client 2. And we can see that on both windows we have the same messages coming. So if both are writing, we have really a broadcasting chat in real time. So that was a quick demonstration how to build not very sophisticated but already advanced system just by joining Flume and Kafka and make it highly available and distributed. This step will do more sophisticated thing than in the previous one. So instead of running a chat, we will really try to pump the data from an API from the web from the meetup that we used during our first session. So there is an API where you can in real time get the data. We'll push it through Flume agent to a Kafka broker, and then from the Kafka broker we will sync it to HDFS as a partitioned directory structure based on the time. Okay, so in order to do it, let's move to our third step. And first of all, we will set up Flume agent that is able to read the data from meetup URL and can sync them to Kafka. So first of all, let's have a look on the agent configuration. So what you can see here, of course, as in the previous one, we have a sync to Kafka, which is described here. It's nothing fancy, nothing has changed from the last time. What is really interesting in this case, because we will implement our own source, which is meetup source, and we'll use this class, which basically takes the following arguments. So stream API source is a generic class that is able to connect to whatever web URL that is producing data in real time. And we set some arguments like the batch size, and which is custom for our implementation. You will see in the source code. Additionally, because we want to partition data by time, we add extra interceptor, which is a built-in interceptor that automatically we will add to our Flume messages in the header a timestamp. This will be important for syncing the data, where based on this timestamp we'll put the data into right partitions. Okay, so let's have a look on the source of our source. So it's here. So the most important thing here is to implement. So basically, you need to implement a class which extends abstract source and implements the following interfaces. In practice, means that you need to have a configuration method. I will not go into details, it just sets the parameters, and this method is the most important one, the process, because here we are really reading the data from meetup and push them to a Flume channel. So first of all, we connect to the Flume channel, and then we have a reader, and then we read in a while loop lines one after the other. So this is basically we are feeding the lines with the data from the meetup stream from the web, and then we finish it until we reach the maximum batch size that we set up in our configuration. So once we have, and we populate the array of events with the data read from the stream. So yes, so we basically build an event from the data from the line, each line. And after that, all we have to do is just to get channel processor and feed it with our array of events. And that's it. Then the data are pushed. The rest is just some logging information. One thing which is important here is that once this entire batch, because this code represents the logic of a single batch, succeeded, you should return status ready. If it didn't succeed, normally you should return status back off, so the same thing will be repeated again. So coming back to connection, this is just a standard connection to certain URL to start an input stream reader. So this is actually the source of our data. Okay, so that's it for the explanation of the implementation. Then we can just compile it. We managed to compile it, great. And well, what we can do, we can just start our agent. Oh, do I have it? So I will start it in a background. So I will redirect the output. We don't want to have too much on our console. So I will redirect everything to that node. So this will start our agent, and already we should see some data coming to our Kafka. So we can also, now we will start the Kafka consumer. So we should see already data slowly coming from Meetup. And then we need to start another session. I will start yet another session to so right now we have messages coming to Kafka, then we want to sync them to HDFS. Yes, so this is another step, which is Meetup. Which is Meetup Kafka to HDFS. There is nothing to be compiled, only what is interesting can be found in the agent configuration. So, as you can see, the source in this case, we have set Kafka source, channel is memory, and the sync is HDFS sync. Yes. So, regarding the source, there is already provided source, so it's built in. We don't have to implement anything. We just need to provide the information where zookeepers are. I will update it a little bit since it changed. And basically, and provide the topic that we want to read from. Once this is done, the Kafka part, the reading part is done. Then what we can look at is the HDFS sync, but honestly there is nothing special except that we are writing to a partition directory structure on HDFS, which is expressed here. So basically what we are using meta characters on the path, which those meta characters are typical for this sync, and then this means that basically they will be replaced by extracted year, month, and the day from the header of each message. So this is the trick to get the data partitioned. And the rest is, the roll count means after how many messages the new file will be created within each partition, and what is the maximum size of the file after it should also be a new file should be created. So by this you are controlling how fast the data are accessible, they are dumped into HDFS. What is the latency of them? Okay, so this is done. So let's run the agent also in background. So I will set it to dev null, the output, and so let's have a look if the data are still coming. Yes, it seems they are. Kafka, and then what we can do, we can have a look on our directory on that it should be here. Okay. Okay. We can see that the directory is actually a little bit hidden. It's here. So this is our directory when Flume is writing data directly from Kafka. So I will copy it and paste. Then of course we have a month. So we can see that the partitions are correctly created. And we can see that inside of it we have files created since 2 minutes already. So let's have a look what is if they contain our data from Meetup. So I will just cut them, one of it, so the recent one, or maybe all of them, why not? Shouldn't be much data so far. Okay, here they are. At the same time we have live stream accessible in Kafka, and every couple of seconds the data are coming into separate direct files on HDFS. They are sync. So we can have a batch processing on HDFS, and we can attach even some streaming analytics to a Kafka system. So this is actually what is the potential of this combining those two technologies for the ingestion. So you can have the access in real time to your data. Okay, so that's it for this step.
So after deploying the previous architecture, that was the one that I'm showing right now, where we had 2 agents. Now we are trying to simplify this by using Kafka, but as channel. So the idea is similar, the data flow is quite similar, but we will not have 2 agents, and we will not have on each of them a channel as memory, which is not very reliable. As soon as the agent fail, we will lose the events that we have in these memory channels. No, we can use other types of channels as file or some another ones that are, for example, JDBC, but we could use as channel also Kafka, which is distributed, which is much more reliable. So this is what we are going to do in this next use case. We will consume from Meetup using the streaming API source that we have implemented. We will configure the channel as Kafka, and then we will write this. We will consume from the channel, so from Kafka with a HDFS sync, and we will write it to HDFS. So this is the fourth use case, and here we can have a look at the config agent. Okay, and what we can see is that we have the same source as before. So the streaming API source, that is a custom source that we have implemented. And then what is special here? Well, the sync is basically, well, before we were using partitioning. Here we are just writing directly without using it. We are just writing directly to that directory on HDFS. But what is special here is the new channel that we are using. So we specify, if we want to use Kafka's channel, we need to specify this class. This is built in, so we just need to specify this. There is nothing to implement. Then we need to specify the topic where the events that goes to that channel are written. In our case, it will be Flume agent, and username will be automatically replaced. Then we specify the broker list, and we need to specify also the Sqoop nodes. Why? Because we need to read, so we need to write and also to read. So we need to produce and consume from the topic. So the Sqoop nodes has changed, so we need to change them also in the configuration. So now it's 3 and 11. Okay. So then in source, so we have our custom implementation for the source, and we would need to compile that. Once we compile, we could start the agent, and we pipe the standard output to null in order to avoid all the messages, and then we run it in background. So it will take some time to start, but as soon as that start, we can check, we can see if in our let's say Kafka topic we are getting the data. No, it will be our channel now. We need to also edit this because of the zookeeper nodes that are different. So we have 3 and 11. Okay. And basically we can start consuming from the topic which is acting as channel, and we can see here how events are coming. If we see carefully, we can observe some strange characters which were not there before, and this is because events now are not written as in the previous example. Here they are written as Abro records. So there is an Abro record which contains a string with all the data. Well, it's a byte array, but we can read a byte array of characters perfectly, but we notice some special characters. It implies that if we want to consume from this channel, we would need a kind of a special implementation. No, we cannot just read let's say the data as a string and that's it. But Flume provides a class that is able to read that record, so it's not a big deal, but it's something that we need to take care of. So messages are going through our channel, but are going also to HDFS. So if we go to HDFS meetup data, in that folder we have also the partitioned data inside here from our previous example, but we can see also data here. This is the data that is coming right now from the Flume agent that is running right now. So we can see perfectly how data is coming. We can check this recent file that was written in the last minute. We can show the content of this file, and basically we have here data that is continuously coming and producing that files. Okay, so that's it for this use case, and then we will move to our last use case. So our last use case will imply the use of HBase. We have seen that the HBase is a NoSQL database where we can store, we can index our data. So we could be interested in storing our data on HBase. So we can do that also by using Flume as data transfer engine. So our last use case will be to move data that is consumed in a streaming manner from Meetup through a Flume agent. We will keep using Kafka as channel, but okay, it is not providing anything new here, but it's, as we know, it's a reliable channel, and then we will store this data. We will sync by using the HBase sync, the built-in HBase sync to HBase. So if we go to our folders, we go to our fifth and final example, where we can have a look at the configuration of the agent. So what we have here, okay, I will need to edit, so I can edit on the way. So what we have here is, as previously, we have the source from the streaming API from Meetup. Then we have the channel in Kafka, as in the previous example. And then what changed here is our sync. The sync is it will be edge-based. We are saying that we will use the Kafka channel, and then we need to specify the table where we are writing to. In that case, the table will be named meetup Flume and our username, but that will be automatically replaced when we run the agent. Then we specify the column family where the data is going to be stored, because on HBase you have data is organized by column families. So the one where it will be stored will be called event. Then we specify a serializer. Okay, we have different options, but that one is quite simple, just to store the data as it is on HBase. And then finally we specify a batch size, so every 10, in that case, every 10 events, it will dump the data to HBase. Okay, so since we are using our custom source for the Meetup API, we need to compile. Then we need to create the HBase table before being able to write to that table. Probably it will complain because it's created already. Exactly. So if you do it the first time, it will be created. In our case, it was already there, so basically we just the table is already there, so we are able to write to that table. So we can start the agent. We can do it in background. So run agent. We pipe the standard output to null, to the same target. We run it in background. So after a few seconds, we will have the data on HBase, and we can check that data if we run the HBase cell. So by running it, we will have an interface with the data that is on HBase, and we can use the scan command to scan any table. So we can scan the table that we are writing to, meetup, data, the username. I would say it was not called like that. Okay. So it was called, let's check in the configuration, meetup Flume dilance. Okay. So we go back to this HBase cell, and with the scan command, we can scan that table, and we see how how the data is stored on the table, where we have the key that is produced by this parser, and then we have all the data to every event that we are receiving from the API. And that's it. It was our last use case. I hope you enjoyed the tutorial, and then you will have also the recording for the presentation. So if you need any other detail, you can go there and also check. We will follow the same instructions and the same use cases. So thanks for watching, and bye bye.